do. Okay, perfect. So I will start the lecture now. So if we can start registering, recording this. Okay, so yesterday I was starting to talk about the principal component analysis, which is a model reduction technique, a linear model reduction technique or data visualization technique, depending on what you want to do. And so today we'll go in full detail and I show some examples. And then after that, we are going to look at another dimension reduction technique, which has slightly different objectives from PCA, and that's the linear discriminant analysis. So, but later about that. So now I'm going to give you a recap of what I was saying yesterday on principal component analysis. Okay, so let me see if my screen is okay. Yeah, here we go. So sorry. So what was the goal? So we have data, and in this section of the lectures, I'm assuming that my data is real data. So we have n components for each data vector, and those components are sometimes referred to as attributes in data science. And so we would like to basically look at the data somehow, but it's a high dimensional data, so it's really hard to visualize. The other objective is that if we have some redundancy in the data, or components or elements which are not important, or attributes which are not important, I would like to reduce them. But how can I identify linear combinations of attributes which are not pertinent? So this is the question. So here was an example. So we have a three-dimensional data X, but it turns out that this data is actually two-dimensional, but it is embedded in a three-dimensional space. So this particular case is such that I know that there are two components, Z1 and Z2, which completely explain the data. And so if you think what that means is that the data somehow lies in a hyperplane in the space. And since I have given this matrix A, I know, of course, how to find that hyperplane. But if nobody tells me this matrix A, so there's no functional form of how this data is formed, so how can I find that hyperplane where my data lives? So this is the question. So I would like to get rid of redundancy in the data. And so in this case, in this example, since I know what the data looks like in 3D, I find two vectors so that if I take the components along those vectors, I get back my Z1 and Z2, and the problem is completely resolved. But this is not the case usually when I have this data. So what we start doing is we use matrix techniques, and so we organize our data into a big data matrix. So it is an n by p matrix. I'm trying to use these n and p exactly in this way throughout these lectures. So n refers to how many components we have in our data, and p tells me how many data points do I have. And so data is arranged in a matrix of size n times p, and typically in data application this p is larger than n, but not always. Okay, so what I'm doing first, I'm removing the mean of the data, and I will discuss later what that means and why I'm doing it and what happens if I don't. So at this point, just take it as a standard operation that I'm doing. So I'm calculating the mean value of my data vectors, which is this x bar, and then I'm subtracting that x bar from each data vector. So what that means geometrically is that I'm moving the cloud of my data around the origin, the coordinate origin. So now the data is around the origin because I have moved the center of mass. And if I have this matrix xc, which is the centered data, so then the centered vector xjc is obtained by just multiplying xc from the right with the canonical coordinate vector ej, which is a vector which has zeros everywhere except for 1 at the jth place. So that picks the jth column of my matrix xj. Okay, so then we do the lean singular value or thin singular value decomposition of xc. So I'm finding the singular values which are non-zero. So sigma 1, sigma 2, etc. sigma r are non-zero singular values, and after sigma r, all the singular values are supposed to be 0. So I'm retaining from the singular value matrices u, d, and v only those parts that correspond to non-zero singular values. So I'm picking the r first columns of ur and throwing away the rest. From VR, I'm picking the R first columns and throwing away the rest. So this way, I am containing all important information of my matrix XC in a compact way, so that I'm not keeping singular vectors that correspond to 0 singular values. And so if I'm looking at the jth column of my matrix XC, remember that column was obtained by multiplying from the right with the canonical basis vector EJ. So what I get is UR times CJ, where the CJ is what is left, which is DR VR transpose EJ. So this here, this matrix C, this vector ZJ is called the principal vector of principal components of the jth data vector. And I'm trying to make this even clearer later so that you see what this principal component means. So the important message looking at this formula XCJ equals URCJ is that the jth data vector, and so now I forget that this is centered, so you can think this is just a data vector. So the jth data vector is a linear combination of the R first columns in the matrix U. So every data vector is a linear combination of those R vectors, which are in the columns of UR. So basically those R columns of the matrix UR are enough to represent the whole data. So that's the point. And so here is a maybe a more suggestive way of writing this. So if I take the jth data vector, so here you see that it's a linear combination of U1, U2, etc. UR. So these are the columns or the singular vectors of the data matrix. And so then there are some components, coefficients, Z1J, C2J, etc. CRJ. So there are R numbers which are related to the jth data. And so those R numbers are called the principal components of XCJ. So the principal components are telling in which way my jth data vector is obtained by taking a linear combination of the so-called feature vectors. So the feature vectors are these UL vectors, which are featuring the whole data. So the whole data can be described in terms of these feature vectors. Now, if I know the feature vectors, and you want to find the singular, so the principal component. So we don't have to go back to the singular value decomposition if the feature vectors are given, because these feature vectors are mutually orthogonal. And so therefore, if I have the jth data vector and I take the inner product with the L feature vector, that automatically returns the Lth principal component. So we are just using the orthogonality of the feature vectors to get back to singular, the principal components. So principal components are obtained simply by basically projecting to these one-dimensional spaces spanned by these feature vectors. So the feature vectors contain enough information so that you can calculate back the principal components. You don't have to know what the singular values are. You don't have to know what the other singular vectors V, L, R. If you have the data and you have the feature vectors, you can calculate always the principal components by this inner product here. And that's useful. So here's another sort of visual picture of what is going on. So there's nothing new on this slide. It is simply so that you see visually what's going on. So we have this XC matrix, and so here are the R singular vectors which I now from now on I call feature vectors. So I have in the columns U1, U2, etc. UR. Then we have the diagonal matrix where the non-zero singular values are on the diagonal, and then we have this matrix VR transpose where the rows are the transposes of the vectors from V1 to VR. And so then I'm multiplying this diagonal matrix and the V matrix, and I get a matrix which is of size R by P. So remember, my data contains P columns, and so this product has to contain P columns too. So here I have R by P matrix, and this is the matrix that contains the principal components. So now you see sort of visually how this matrix product looks like. So we have the feature vectors here in columns, and then the columns of the second part, this Z matrix here. Those are the principal components of my data. And so if you know the feature vectors, you can characterize your data by these principal components. So you see that I have reduced the size of my data. So originally my XC was an N by P matrix. Now if you look at this principal component, this is only R by P. And so typically there are less rows in this Z matrix than there are in this X matrix. Okay, so this is the setting, and so I'm showing basically the same things over and over again, but these are all kind of a slightly different views of the same thing. So I hope this is helpful. So my principal component matrix Z is a matrix whose columns are denoted by Z1, Z2, etc., ZP. So I'm trying to be systematic, and when you see an upper super index in parentheses, so typically that means that I am referring to a vector. And when you see a subindex, that's typically when I'm referring to a component of a vector. So these Z1, Z2, etc., ZP, these are vectors of length R. Okay, so these are the principal component vectors of my data. And as I pointed out, this Z matrix can be obtained by just taking inner products with the feature vectors. So effectively, using the matrix language, if I have the data X, I just multiply by the transpose of UR, and I get the principal components. Vice versa, if you have the principal components, you can get your centered data by simply multiplying UR, which is the matrix of feature vectors, by the principal components. And then if you want to go back to the really original data, you just add the mean value. And so then you get back. So you see that here we are not losing any information. So this is one-to-one relation. So if you have this principal component of feature vectors, you can always recover your original data. So here we haven't reduced the dimensionality by throwing out anything. We are just reorganizing things. So this is sort of a compression of the data. So we are trying to be as economic as possible here. Okay, so now let's look at these the sizes of these principal components first of all. So for now I'm not writing the subindex C here to remind that my X is centered. So you can have this, you can think that this matrix X is now the centered data, so that I don't have to think about this X bar, which is the center of mass or the mean of the data. So we have this sort of layered view of the singular value decomposition. So this is one way of writing the singular value decomposition. X can be expressed as a linear combination of rank 1 matrices, UL, VL transpose, and the coefficients are the singular values. Now, if this is the representation of X and I go back to, let's say, to the jth data vector xj, I multiply by this canonical basis vector, and here things are written out, so I get VL transpose EJ. What does that mean? It picks the jth component of my vectors Vj. And so this is nothing else but another way of writing the decomposition of my jth data vector in terms of the feature vectors. And of course, these coefficients here are the principal components of the data vector xj. So looking at this formula, let's see how large these principal components are. So I'm taking the scalar ZLJ, which is the lth principal component of the jth data vector. So by definition, this ZLJ is sigma L VJL. Now, here we have the jth component of the lth basis vector. The jth component of the lth basis vector can never be larger than the length of the vector. So if one component cannot be larger than the total length of the vector. So therefore, I have an upper limit for this absolute value here, given by sigma L times the length of the lth vector VL. But now remember, in the singular value decomposition, these VLs are normalized, so their L2 norm or Euclidean norm is 1. So actually here should be an identity, not smaller or equal. It's not wrong, but we know that this length is 1, so there should be an identity here. So sorry for that. But the important thing is that I see that the lth principal component of any data vector is bounded from above by the lth singular value. So these principal components cannot be large if the let's say they cannot be arbitrarily large. They are bounded by the singular values of the data matrix X. So that gives us another view of what these singular values are. They are somehow measuring the size of my data. So this is an important upper bound. So we know that. And so why is this important? When we are reducing the data, we need to know how much error we do when we are sort of throwing away some information of the data. So here is the idea. Model reduction. So what I want to do is, suppose I have 100-dimensional data, and I want to understand how this data looks like, and I want to do some calculations with the data. But my algorithm is such that it cannot handle 100-dimensional data. So somehow I would like to retain the essential features of my data, but reducing the dimensionality of my data. So suppose my algorithm is such that it handles easily 10 dimensions. So I want to throw away 90 dimensions and keep 10 dimensions of my data. But so then I need to figure out which dimensions I'm throwing away. And I'm trying to do it in such a way that I'm controlling how much error I'm doing when I'm doing this approximation. So that's model reduction. And so here we are. UK is now a matrix where I'm retaining k first feature vectors. So I decide, let's keep only k feature vectors. Remember, I have r feature vectors, so this k here is less or equal to r. And so I'm deciding to use only k feature vectors. Now, from my lecture of yesterday, when I was talking about the linear algebraic background, you saw what the orthogonal projection matrix looks like when you have orthogonal bases. And so these u vectors are orthogonal. So now I'm projecting on k first feature vectors, and so the projector is UK transpose. So this is the projection matrix. So what does it mean? If I have a matrix xj, vector xj, and I want to find the projection on the subspace spanned by the first k singular vectors, the vector which is in that subspace is obtained by pk times xj. And in general, my xj using singular value decomposition is a linear combination of the r first feature vectors. So when I'm projecting, I'm retaining only k first feature vectors. So the projection operator is such that it retains only k first feature vectors of my representation of xj in terms of the feature vectors. And of course, these coefficients here, they are nothing else but the principal components of xj. Okay, so projection to a lower dimensional space using feature vectors means simply that we are discarding some of the feature vectors away. And so now the question is, how large an error do we do when we do the discarding? So here's another view. Okay, so here is my xj. xj is, in general, it is a linear combination of the feature vectors, and the coefficients are the principal components. There is a 1 missing here in this zj, so this is the first component. So when I project to the k first principal directions or feature vectors, I'm keeping the k first components and I'm discarding the rest. So therefore, if I'm asking how large an error I am making when I'm projecting to the lower dimensional subspace and reducing my data, it is given by the norm xj minus pk xj. And I'm calculating here the square of the norm. Okay, so now we see that since xj is given by the full sum and pkxj is given by the sum up to the index k, so then the error is the remainder. So L is running from k plus 1 to r. So this is the approximation error. And the norm of that approximation error is given here. Now, ULs are mutually orthogonal and they are orthonormal. So if you now calculate the norm of this vector here, since we have orthonormal basis UL, this norm is equal to the square sum of the components. So here I'm using the orthogonality and orthonormality of ULs. So we see that the error that I'm making here when I'm discarding the remainder is simply the sum of the principal components running from k plus 1 to r. So now let's go back. 2 slides ago, I told you that the ZLJs are bounded by the singular values of the matrix X. So I get an upper bound for this sum, and this sum is simply L runs from k plus 1 to r of the singular values squared. And so what is nice here, this upper bound does not depend on j. So whichever data vector I'm looking at, this is the absolute upper bound for everybody of them. So this is independent of which data vector I'm looking at. And so this is a general upper bound. And so if this number now is small, then I can safely say that, well, I'm not making a big mistake a big error if I'm just looking at the lower dimensional projection of my data. So how do we choose this k in general? So if you need to do data reduction and you have to cut somewhere your representation of xj's in terms of the feature vector, so how should you choose this k? Well, here's an idea. So this is something which is referred to a discrepancy principle. So suppose that your data is noisy. So suppose you are measuring, let's say, you know, the temperatures and humidity and that sort of thing. So you have all kinds of data which contains error. So your data is always somewhat inaccurate, and you often have some idea how inaccurate your data is. So you have an idea what sort of noise level you have. So if you know that your data is noisy and the noise level is described by some number tau, you can argue that any approximation of xj which is within the error limit is an acceptable approximation. So if your xj is known up to an error which has norm equal to tau, so then if I approximate my data vector xj by something which is within that noise level, so you can safely say that you are not, let's say, creating a bias in your data, because you can argue that x hat is an equally good approximation of the truth, and so therefore you would like to have an approximation which has the property that is closer to xj than the error level. Now we know how large this error is if xj hat is taken to be this projection. So let's call this pkxj. Let's call it x hat. So how should I choose my k so that this condition is valid? Well, I should choose the k to be the smallest possible value so that you're barely under the noise level. So if you take one less case, then you're above the noise level. But if you throw away the indices from k plus 1 to the rest, then you're below the noise level. So if you choose your k to be the smallest possible k so that this condition here is valid, then you are fine. Your model reduction is such that you have reduced your dimensionality of the data from R to K, but you are still within the error bound of the original data. So you are not losing essential information, so to speak, when you do this model reduction. So this is a good principle, model reduction principle to keep in mind. So I studied this topic on principal component analysis by talking about redundancy in the data. So if you give me data, in general, I don't know if my data is redundant or not. I would like to know that because, of course, I don't want to do computations with redundant data. So it'd be nice to reduce the data to the bare minimum. And so this PCA now gives me a way to detect low dimensionality in my data. And I will show you an example soon. So if I know that my data is, let's say, noisy, so let's say there is this 10 to minus 5 noise level. So anything which is below 10 to minus 5 can be considered as noise. And so when I look at the singular values of my data matrix, and if I find that starting from some k plus 1 to r, the sum of the singular values is below this 10 to minus 5, which was my putative, or squared actually, of my putative noise level, then I can say, well, it looks like my data is actually k-dimensional, because what is beyond that k dimensions could be considered as noise. So this PCA gives me a way to detect low dimensionality of the data. So you're just looking at the singular values, and if you see that the singular values at some point drop dramatically, you say, okay, so let's cut there, and we can assume rather safely that the singular values that are above the cut threshold are the singular values that contain the pertinent information of my data. So we can use this PCA to detect low dimensionality of the data, and we can use it to remove redundancy in our data. And so that was, we are going to look at an example soon. So before that, I'm going to talk about something which is related to the dimension reduction, but it's slightly different view. And this is PCA and data visualization. So when you are looking at data, you would like to find dimensions which are sort of most informative. And so if you want to visualize your data, you want to find projection directions, which are somehow most suggestive, so that you see the characteristics of the data. So here is an example. So suppose that you are looking at shadow images of two objects. So here is a pen and scissors. And so you would like to understand what your data represents. In this case, it's the scissors and the pen. So if I'm taking the projection like in the figure in the left, you see that the pen and the scissors, they look pretty much similar. So in order to understand what my data represents, this would be a bad projection direction for the, at least for the scissors part. The pen, I mean, you can rotate it and it looks more or less the same in all directions. Now, if you take a different projection of your scissors, you see that the real difference between the pen and scissors. So in the figure on the right, we have found a more informative projection direction of the scissors data. And so what's the catch here? So if you think of this object scissors, what we did here, we projected scissors into the directions where the object has the largest possible spread. So when you are finding the direction, the two directions in which the object has the largest possible spread, so then you are likely to detect what the object is. So that's the intuitive idea here. And so we would like to do the same thing with data sets. So if you give me a data set and I project it to a low dimensional space, so I probably would like to have a projection direction where the data is spread out. So if there are clusters, if there are gaps, if there are some topological structures, I would be able to look at that with my eyes. So that's the idea when we are visualizing the data. So we want to find the most informative, visually most informative direction in which we can project our data. And so keeping in mind this scissors example, a good criterion is to try to find the directions where the spread of the data is largest possible. And so here is the idea put in linear algebraic form. So I have a vector q, and I'm taking this q to be normalized so that this length is 1. So length meaning here the Euclidean length, L2 norm. So then I take my data set x, and I'm asking what the component of my data in this direction q is. And so remember, if you have a vector and you want to compute the component of that vector into a given direction, you take the inner product of your vector with that vector where you are projecting. And so I want to calculate the inner product of x1 and q, xq, x2 and q, etc., xp and q. And so that means that I'm, if you look at this second row here, q transpose x1, q transpose x2, etc., you can write this briefly as q transpose x. X is the data matrix, and here my X is supposed to be centralized, but it may not. So I'm going to, as I said, I'm going to discuss a little bit the centralization later on. But so you can think that this X is now centralized data. So these inner products are scalars, and the scalars are denoted now by y1, y2, etc., yp. So I have here a row vector. So my y is uncharacteristically to my notations, y is now a row vector. Okay, so these are the components of my data in the direction q. And so now I should find out a way to measure the spread. So how widely spread my data are, and in this direction. So how widely spread the components of my data are in this direction. And I'm defining the spread as the norm of my vector y. So I'm taking the square sums of these yj's from 1 to p. So p is the number of my data points, and then square root of that. So that tells me more or less how much stuff I have in my data matrix in the direction of q. So you can think that you take your data as a cloud, and then you try to find an intersection of your data where the spread is largest possible, and so you would like to measure how widely spread your data is. You calculate this norm of y, which is the spread of my data in the direction. Okay, so so now the question is, what is the direction q that maximizes the spread? So I want to find the direction in which my data looks as wide as possible. So I want to maximize the spread. So my matrix y is or vector y is a 1 by p matrix. So it is a row vector, and so I'm going to calculate the spread squared. So this is the spread squared which I'm trying to maximize. And so you can calculate this spread squared by taking y transpose. So now this is an inner product because my y is a row vector. So we have a row times column. So this is a scalar, which is exactly the sum of the components of y. And here I shouldn't have n, I should have p. So this is a typo again. I'm trying to correct those typos before I'm posting my slides, which you, by the way, find on the folder, course material folder. So my y transpose plugging in y is, remember, y is x transpose q. Sorry, y is q transpose x, and so y transpose is x transpose q. And so if you look at this quantity here, so this is nothing else but the norm squared of x transpose q. Well, it's clear because x transpose q is y, so that's the norm of y squared. So if I want to maximize this, what does it mean? I'm trying to find the maximal value of the norm of x transpose q with the constraint that my q has norm 1. Now, if you go back to the first lecture of this lecture series, you see that this is nothing else but the induced norm of my x transpose. So that's the induced norm of x transpose. So, and if you look at the matrix and you want to find what is the induced L2 norm of that matrix, it turns out to be the largest singular value of xt. Oh, that's great, because I know what the singular values are. I have the singular values of x. Now the singular values of x transpose are exactly the same. Remember, I had a slide which said that if I have a singular value decomposition of a matrix, I also have immediately the singular value decomposition of its transpose. And so the singular values are going to be the same. And so therefore, the maximum spread is equal to the largest singular value of my data matrix, x. Now this is good news. So we know how to calculate the maximum spread. And so now we only have to find what the direction q is, where this matrix attains the maximum spread. But we also have all the information to do that, namely, if x using the singular value decomposition is written as the sum of rank 1 matrices, then x transpose is easily obtained by transposing this vector outer product. So I get u v transpose will be v u transposed. And so then I'm multiplying this x transpose by this u vector from the right. So here is the product. And so then I see that when I do the transpose and use the fact that transpose is the vector itself, I end up having the inner product of uj and u1. My feature vectors are orthogonal and orthonormal. So I know that this inner product is 1 if and only if j equals 1, otherwise it's 0. So I have this Kronecker delta, which is 1 when j equals 1 and otherwise 0. And so that means that from the sum, the only term that remains alive is the first component. And so you see that x transpose u1 is exactly sigma 1 times a vector which has a unit length. And so forth. Therefore, the maximum spread of y is, which was found to be sigma 1. Sigma 1 is the same as the norm of the vector x transpose u1. So what does that mean? It means that u1, the first feature vector, is the direction in which the spread is maximized. So if you give me a data set and you want me to find the direction in which the data has the largest spread, the first singular vector or the first feature vector is the direction in which the spread is the largest. So that's the direction in which we should look at the data. So if we want to visualize the data, we should look at the let me see, look at the first singular principal component. So the first principal component gives you the largest spread of the data. How about the second largest? Well, we can continue this game of finding new directions as follows. You have the data X, so we already know how the data looks like in the first direction, and so we want to find the second largest projection direction. And so what I'm doing, I'm deflating my data. So I'm subtracting the rank 1 part, which corresponds to the largest singular value from my data. So I'm defining a new matrix X tilde, which is X minus the part that I have already explained, but I'm already explaining. And so that means that this X tilde is exactly like my original X, but the sum here is running from 2 to R because I'm subtracting the first component here. And so in order to find the second largest spread direction, I'm taking this deflated matrix and I'm playing the same game again. So what is the best possible direction Q so that the spread of this Y tilde is largest possible? And since we have the singular value decomposition of X tilde, which is given here, so the singular values are sigma 2, sigma 3, etc. Exactly the same argument as before tells me that the second best direction in which the data has the second largest spread is given by the second feature vector, and so on. So what we can do is, if you want a two-dimensional picture of your data, and you want to maximize the spread of the data in those two directions, so what you do, you take the first two singular vectors, or first two feature vectors, which is the same thing, you project your data on that direction and you look at the principal values, and then you can make a scatter plot of your data. So now your data is two-dimensional and you can visualize it as a scatter plot. And the scatter plot is now such that you have the maximal spread in those two directions. So this is really a useful and nice way of looking at data, and helps you to understand what's in there in your data. So now I go to examples, and so this is my original example, which was the sort of the introductory example. So my data xj is generated by using this model. Xj is A times Cj, where Zj's are two-dimensional vectors, and A is given by this matrix expression here. So I'm generating a data. So this is a little snippet of MATLAB code, and so I'm generating a data of 2,500 data points. How am I doing this? I am generating random numbers z1. So these are the first components of this vector z, by drawing the random numbers from uniform distribution between 0 and 1. So this rand 1p is generating a vector of size 1p with random numbers between 0 and 1. So rand is the command that is generating pseudo-random numbers between 0 and 1. The second component I'm taking to be 2 times rand 1p. So these are independently drawn random numbers between now 0 and 2, because I'm multiplying by 2. So my vectors zj are random vectors where the first component is between 0 and 1 and the second component is between 0 and 2. And so then I'm forming my data x, which is a three-dimensional data, so that the first component is z1, the second component is z1 plus z2, and the third component is z1 minus z2. So this corresponds exactly to this matrix formula here. So my data is essentially two-dimensional, but with this matrix A, I have embedded the data in a three-dimensional space. And so now I throw away this matrix A and I say, well, given this data, can I identify the directions in which this data looks two-dimensional? Because it should, because the data is organized along a plane, but I just don't know what the plane is if I don't know this matrix A. So this process is now hidden, and we don't know how the data is generated. We are asking, can we reduce the dimensionality of the data? And so here is the PCA algorithm. So So let's go step by step. So first of all, I'm going to center the data. So my X bar is going to be the mean value. So I'm taking the sum of my X matrix in the second direction. So this 2 here means that I'm summing column by column by column by column. So I have P columns. So the outcome is going to be a vector of length 3. And I'm dividing by P, so this gives the center of mass. I am subtracting from each column of X the same column X bar. So I'm forming a rank 1 matrix where I take this column vector X bar and I'm multiplying by vector 1P. So this is a vector which is of size 1 times P, and it is just replicating this X bar. So there's in MATLAB, there's another command, if you are familiar with that, which is called repmat. So you can form a matrix which is replicating this column. I like to use this expression because I feel that I have more control on things, but that's my my taste. Okay, so then I'm calculating the singular value decomposition of this XC. And so the command in MATLAB is svd XC, and so you get U, D, and V. Now sigma is giving me the singular values. So I take the diagonal entries of D, so there are 3 numbers here. And so it turns out that 2 of them are non-zero and 1 is 0 because my data happens to be 2-dimensional. So if you do this and you check what these sigmas are, you get 2 non-zero values and the third one is 0. So that's an indication for you that actually your data is 2-dimensional. So I didn't print it here, but please do and check that this is the case. So you can go and do the simulation yourself. Now I want to compute the first 2 principal components. So what I do, I take this U matrix and I'm retaining the first 2 columns. So I'm retaining columns from 1 to 2, all rows, but only 2 columns. I'm taking the transpose of that and I'm multiplying by the transpose, my XC. And so these Z's are now the principal components. So this Z is now 2 by P matrix. So the first row gives the first principal component and the second row gives the second principal component. And so then I make a scatter plot where I plot the first principal component against the second principal components using black dots of size 10. Here is something which is just to make the fonts readable. And then in order to see what I really, because this is 3-dimensional data, so there is a way to look at the data also in 3 dimensions. So I'm using a scatter plot in 3 dimensions just to see what my original data looks like. So if you have more than 3 dimensions, this one you cannot do. But since this is a toy example, I have 3-dimensional data, so I can look at what the data looks like. And so here is how the outcomes look like. On the left, you see the 3-dimensional plot. And indeed, you see that your data points are distributed in a planar fashion. So all the data is in a 2-dimensional space. So if I had a live MATLAB demonstration, I could rotate, and so you'd see that the data are really distributed along a 2-dimensional plane. So this tells you that the data is 2-dimensional. The way you see it mathematically is that you see that only 2 singular values are non-zero. And here is the plot of the principal component. So this x-axis is the first principal component, and the second axis is the second principal component. And look that this is really in line with what we were doing. So the spread in the first principal direction should be largest. So the spread here is from about minus 1.8 to like maybe 1.8. And the spread in the second direction is smaller, so it is from minus 0.7 to 0.7. So you see that indeed the x-axis corresponds to the first principal component because the spread is largest, and the second one is corresponding to the second principal component because the spread is slightly smaller. And if you would take a projection to the third component, you would get 0. So there is no spread in the third direction because the singular value is 0. So if I would, stupidly enough, try to plot, let's say, the first principal component against the third principal component, my axis here would be something like 10 to minus 12 or something. So because there is nothing happening in that direction. But so see how nicely this principal component analysis is figuring out in which direction you should look at the data. So you can think that you are here in the 3 space and you are trying to find a way to look at your data so that it has the maximum spread. And the singular value decomposition automatically puts you into a position where you are looking face down the 2-dimensional data, and this is the projection. So the principal components they're the great way to visualize data. And so how about the centering? So I said that the centering is often done, but it is not necessary. So here is an example. So suppose you have a normally distributed cloud of points. So I have component x1 and x2 are normally distributed. So I'm using rand n. I have 1,500 points. And the spread in the first direction is 1, and the spread in the second direction, so the spread not, but the let's say the standard deviation, if you want to use the statistical term, is 0.2. So my data is spread in 1 dimension more than in the second direction. And then I'm moving my data out from around the origin to be around the 0.44. So this is my data. And so if I do as instructed before, the first thing I would do is to center my data. So I would subtract the calculated mean, which in this case would be more or less 4,4. So if I calculate empirically now the center of mass, my center of mass is not going to be exactly 4,4 because this is numerical data, but it's going to be close to 4,4. And so then I can subtract my data, and then I have this nice Gaussian cloud. But now my cloud is moved away from the origin. So what happens if I calculate the principal components with or without centering? So here is what happens. The red picture on the right, that's what the principal directions are if I do centering. So the first principal component is pointing in the direction in which my data has the largest spread. And the second component is pointing to the direction where it has the second largest spread, which is orthogonal, because the feature vectors are always orthogonal. So this is how the directions look like. The principal directions look like in this case. If I don't do the centering, what happens is that now I'm asking in which direction, looking from the origin, which is here, there is the largest spread in data. And so if I don't do the centering, my first principal vector is pointing to the general direction of my data cloud. So this first principal component is almost like telling me in which direction in space my data cloud resides. And then the second component has to be perpendicular, so it's going to be this other vector. So if you have high dimensional data, so this is 3-dimensional, sorry, this is 2-dimensional data, so this is kind of a trivial case because you can already look at the data without doing anything. But so if you have high dimensional data, what typically happens if you don't center your data is that your first principal component is kind of wasted because it is just telling in which direction in space your data is lying. And then the second and the third and the fourth, etc., principal directions are telling you about the spread of the data cloud. So therefore, it is often advisable to do this centering. If you want to visualize your data, you don't want to necessarily to waste the first singular vector only to have a pointer in which direction in space your data cloud is. So this is the picture to be kept in mind when you think, do you need centering or not? Sometimes it may be a useful idea not to center. So I'm not saying that you should always center, but if you don't care where exactly in space your data are, so then maybe centering is a good idea. And so then you really get the internal structure of your data cloud using principal components. So you can center or you may not center if you don't want to do that, but remember what the effect is. So this is the message here. And so I think it's a good we have time to go through an example which is a little bit less trivial. So this is a real data example. So I'm using a data set which is really popular, and it is a database data set which contains handwritten digits from the US postal envelope. So classifying handwritten digits is of course important for automatic post delivery, for instance. And so therefore people have been developing data science methods to classify handwritten numbers, which are obviously sometimes very hard to read. So this data set that I'm referring to here is there are several of this type in internet, and you can find reference to some of them in the web page of the book. So if you want to play around with this data set, you can go to the web page of the book and download the data set. So there are, in this data set, there are 1,707 handwritten digits. They have been pre-processed by a human observer, so they have been centered and scaled so that they are sort of comparable. There are 256 grayscale levels, so this is a black and white picture, and it's pixelized rather coarsely, so there is 16 by 16 pixels. There are also databases where you have 32 by 32 pixels or 64 by 64, depending on how much you want to add the dimensionality. So I'm using this 16 by 16 pixelization, which means that so I'm arranging all these pictures as a long vector. So I'm reading the pixel image column by column. So I have 16 columns. You can think that the data is a matrix. Each letter is a matrix, or each number is a matrix. And the matrix entries are the grayscales. And so what I'm doing now, I'm arranging those matrix entries into a long vector of length 256. So that's the number of attributes or dimensions in my data. So my data lives in 256 dimensional space, and therefore I cannot really sort of visualize my data. I can visualize individual data points because they are handwritten digits, but I cannot visualize the data as a cloud. And so then I have also an annotation in this data set, which is a vector ij that tells me which number each vector here is representing. So these ij's are from 0 to 9. So you have numbers from 0 to 9, handwritten numbers, and so they are annotated, and this annotation in this vector ij. So that's the data set. So now I want to look how these data points are distributed in space. So what I'm doing, I'm taking let's see. So here I'm looking just the visualization how the individual handwritten digits look like. So I'm taking one sample from each one of those classes. So my j is running from 1 to 0. So 1 corresponds to 0, and 10 corresponds to 9. So I'm first identifying the index vector of digits that represent the jth digit, and then I'm taking one of them. So I'm taking the first one here. I'm taking the first representative of each class, and then I'm looking at the picture using this image sc command in MATLAB. So first I have to take my xj vector and reshape it again back to a 16 by 16 matrix. For some reason, these digits are lying on their side, so I take a transpose of that. I believe it's because the digits are digitized in lexicographical order rather than column-wise, as I am doing it. And so then I'm using a color map 1 minus gray, so that 0 is white, so that the background where there's no writing becomes white instead of black, using axis square and axis off. And so here you see 10 samples. So this is a representative of handwritten 1, 0, handwritten 1, 2, etc. 9. So the data entries, they look pretty much like this. So they are real handwritten digits, and so this is the coarseness of the pixelization. So let's ask a question: how similar or dissimilar the digits are within each group? First of all, so let's divide first the data set into subgroups, so that x 0 represents the zeros, x1 represents ones, etc. So I'm identifying those vectors which are having the label k, and I'm collecting them into a matrix, and then I'm making the singular value decomposition of that matrix. So here is xk contains only, let's say, ones or sevens, depending on what my k is. And so then these u, k, d, k, b, k are representing the singular values and singular vectors of that group of data. And so if you plot those singular values, you see that, let's look at this center one. So these are the singular values of all data vectors which represent the handwritten 1. And so you see that the singular values, they start somewhere above 1, so 10 to the power 0 is 1, and so then they are decreasing. The singular values are always in a decreasing order, and then at some point there's a total collapse. So after a certain threshold, the singular values are all 0. So what does that tell us? It tells us that the data matrix containing these handwritten ones is essentially representable by roughly 100 feature vectors. Because after that, the feature vectors, the singular values are 0, and there's no information whatsoever. So you can think that instead of this 256 dimensional space, your ones are lying in a subspace which has dimension about 100. So they are all contained into a 100-dimensional subspace. So that's some information. Whereas if you look at, let's say, 5s, the 5s are all over. Because why? Because handwritten 5s are, from one to another, they are very different. And so in order to characterize all these handwritten 5s, you need all the dimensions, 256. So they are not similar to each other like the ones are. The ones are much more similar to each other than the 5s, which is understandable. Most of the people write a 1 as a vertical line. And so there is not much variability there. And so therefore you can explain the data with fewer principal components than what you need to explain 5 or 0. So that's one way of using this principal component analysis. You can look at the information contents of your data. And so here are some principal feature vectors. So if you take the feature vectors are living in this 256-dimensional space. And of course, you can take each one of those feature vectors and plot them as an image. You just arrange the feature vector components into a matrix, and then you use this image SC. And so the first column here shows the first 3 principal vectors of the index 0. Here is 1, 2, 3, etc. So you see that these principal the feature vectors, they somehow they tell you what we are looking at. So they are pointing into the direction where the data are in the space, and so somehow they are capturing the features of your data. And so now if you want, for instance, represent your handwritten 7s, you take these principal components in the row that corresponds to 7, and you start to take linear combinations of these principal vectors, and little by little the handwritten 7 emerges when you add more and more features. So this is the idea. Now here is a question. So suppose I'm looking at, so this is the couple of slides and then we make a break. So let's take 2 of those digits. So let's look at 0s and 1s. And my question now is, can I tell apart 0s and 1s in my data space? And in order to answer this question, what I'm doing, I'm taking 2-dimensional principal component projection of my data. And I'm trying to see if the data forms some sort of cluster. So if zeros are in one place and the ones are in another place. So what I'm doing, I'm taking the index vector II, which is containing the indices where the annotation is either 0 or 1. So I'm keeping pointers to the data vectors which represent either zeros or ones. And then I'm taking my full data X, and I'm keeping only those columns which corresponds to zeros or ones. So what I'm doing here, I'm taking all the rows, but only columns that corresponds to zeros or ones. So my Y is now my data. And so then I'm centering my data here. So I'm taking the mean value of my y's, and then I'm subtracting the mean value of my y's. So the yc is now the centered data. Exactly as we did before, I calculate the principal value, singular value decomposition of my centered data is here. Then I take the first and the second feature vectors, and I'm taking the components of my centered data in those two directions. And so now my z is the reduced data. So it is containing the two first principal components of this data set. So this z is 2 by p matrix, and p is the number of ones and zeros in my data set, which I don't know right what it is, but it is several hundreds, I believe. And so then I'm doing the scatter plot of the first and the second principal components here and checking how my data looks like. And so here is the outcome. And so I have not marked the zeros and ones using different notations here, but I'm telling you what happens. So this tight cluster here, those are the ones, and the zeros correspond to this wider cluster here. So when I see this picture, if I don't know what my data represents, I would start to think that maybe this tight compact cluster here represents one feature or one, let's say, subset in my data set, and the spread out cluster would represent another subset in my data. And indeed, if you go and look at, so you pick points that correspond to the points in this compact cluster, you will see that those are ones. If you take any one of these points here in this spread out cluster, it turns out that those are zeros. So this principal component analysis of this data gives me immediately some information about the, let's say, the topology of the data in some sense. So how the data are distributed in space. And so that helps me to do further steps when I'm for instance starting to do an algorithm which is classifying my data. So seeing this picture tells me that the classifier should not be doing badly if the classification problem is to tell apart zeros from ones. So there obviously is some sort of topology in the data which helps me to do this classification. And I realized that it is 7 minutes past the hour or 8 minutes past the hour. So maybe we can make a small break here so that you don't get too tired. So let's continue at 4:20. So we have 12 minutes time to stretch our legs and get together. So 12 minutes break. Thank you.
Okay.
Thank you.
Thanks.
Okay.
See you.
Okay, so it's 20 minutes past the hour, so I will continue. And so there was I looked at the chat box, and there was a question whether it's possible to get the slides in advance, and I'll try to do that. So that's a good idea, so that you can look in ahead of time. Only warning is that I'm updating my slides at the last moment. So if I don't have the slides ready in advance, then of course I have to do it later. But so I'll try to do that at least the day before, so that you can go through the material in advance and you know.
Okay, Prof. Thank you.
All right, good. So let's continue. So the next topic that I'm going to is linear discriminant analysis, which is another projection method besides PCA. And so here the objectives are different. So we are not trying to find the directions in which the data are most spread out, but in this case we assume that we have annotated data. So we have, like in the case of handwritten digits, we have some test data where we already know that the data consists of subsets. And then we try to find the most informative directions where we can see whether the data are different from each other. And why would we do that? So if you are given data, and so you have a training data, and then you have the real data, which you try to classify. So the first question that you might want to ask is there enough information in my data so that I, at least in principle, will be able to distinguish between the groups in my data? So, and LDA gives me a good way to assess that answer. So linear discriminant analysis goes back to Ronald Fisher, who developed it using statistical language. And so if you go and look at linear discriminant analysis in statistics books, it looks rather different from what I'm telling here, although we are talking about basically the same thing. So in statistics framework, usually there is a reference to underlying normal distributions and means and covariances and heteroscedasticity and things like that. So I'm not doing anything of that. So my data is just a cloud of points in a high dimensional space. And you will see. So as before, my D set is the set of data points from x1 to xp. So each one is a vector of length n. And so then I'm assuming that my data consists of disjoint classes, D1, D2, etc., dk. So we have k different classes, so that these classes are not overlapping. So we know exactly that each vector belongs to one and only one class. And this annotation vector ij is telling me which class we are in. So if xj is L, that means that the jth vector is in the Lth category or class or cluster, whatever you want to call this, DL. So think about the handwritten digits. So D1 are the handwritten ones, D2 is the handwritten twos, etc. And so we, in our training set, we know in which class each one of these data points belong to. And the question that we are answering here is, can we find a low dimensional projection direction or directions of the data so as to maximize the spread between the classes? So now we want to see not how spread out the data are, but we want to see if there's a way to find gaps between those clusters or classes, D1. And so here's a preliminary example. So suppose my data is two-dimensional, and so it consists of two classes, and since I have the annotation, I can tell that one of the set is consisting of red points and the other one is of green points. And so if you go and take the principal component projection of that data, the principal component direction, the first feature vector is going to be this blue vector here, and so that spans a one-dimensional space, which is this dashed line here. And so if I plot all my data to that direction, so I take the component in that direction, and then I plot my data using histograms. So that's what I get on the right-hand side. And so what is significant here is that the histograms are overlapping. So I cannot really tell apart the green histogram and the red histogram in this case. However, if you look at this picture here, so you would intuitively say that if I'm projecting into almost an orthogonal direction here to this blue line, then I would clearly have two nice compact clusters. And maybe that's the direction that I would like to use here. So the principal component analysis is not doing what I want here. And so this is the whole idea, the linear discriminant analysis. So let's think about what would be characteristic for the line that is perpendicular to this blue line. Well, first of all, both of those clusters would appear as compact as possible, right? Because that's the direction where you see not the spread of the green dots, but the green dots would be in one place, and the red dots would form another tight compact cluster. But the mean values of those two clusters would be as far as possible from each other. So those are the two things that I would like to encode in my algorithm to find that informative direction. So let's start to develop these concepts. So first of all, remember that we defined the spread. So if you have a data matrix X and you take the component in the direction Q, you get this row matrix Y, which is Q transpose X. So this is a row vector consisting of components of the data in the direction Q. And so then we define the spread of Y to be the square sum of the components of Yj, so which is Y transpose in this case. And so then I'm plugging in my Y here, so it is Q transpose Q X transpose Q. And so what I'm doing here now is I'm taking this matrix X transpose. That's an n by n matrix, and I'm denoting it by S. And I'm giving a name for that matrix. I'm going to call it the scatter matrix. So those of you who come from statistics, you realize immediately that my scatter matrix is somehow related to the covariance matrix, if you like. So there is immediately there's some sort of hint of statistics here. But so I'm not referring to as a covariance matrix. I'm calling it the scatter matrix. First of all, my data are not centered here. So this is just any cloud of points. So scatter matrix is this S here. However, I'm going to center. So here is the story. I take my data and then I'm organizing it according to the annotation. So I'm organizing the data vectors that correspond to class 1 in the first block. In the second block, I'm organizing the vectors that belongs to the second class, etc. And the last block contains the kth category data. So this is like partitioning the data. So but using a permutation, I organize so that first comes the data corresponding to annotation 1, and then data corresponding to annotation 2, etc. So XL in general is xj1, xj2, etc., xjp, where these indices j1, j2, jpl are pointers to vectors that belong to the lth class. So IL is going to be the index vector that tells me which points belong to the lth class, and XL is the actual data. And so this matrix here has dimensions n times PL. PL is the number of data vectors in the class L, and the sum of those P1, P2, etc., Pk is equal to P, which is the original size of the data. So this is just an organization of my data. Nothing fancy here. So my data is annotated, remember. And so what I'm doing now, I'm taking each one of those clusters. I'm calling them clusters, although I don't know really if my data is clustered. So this cluster is just to keep my sort of. So I'm thinking of this picture. So the green cluster and the red cluster are the subsets of the data. So I'm referring to the subset as clusters. So I'm calculating for each cluster the centroid or center of mass. So I'm taking the average of my data vectors which are belonging to the lth cluster, and then I'm centering my lth cluster. So I'm taking all vectors which belong to the L cluster, I'm subtracting their mean value from them. And I will show you a figure what I'm doing here. So this is the centered L cluster. And so this way I get something. So when I'm collecting these centered clusters into a matrix again, so then I have what I call a within cluster centered data. So this W refers to the word within cluster. So each data cluster has been centered, and then they're collected back into a big matrix. And I believe a picture tells more than the words. So here is a two-dimensional schematic picture what is going on here. So I have data consisting of three separate clusters, the red ones, the blue ones, and the green ones. So first of all, for each cluster, I calculate the cluster mean. So the black dots that you see in the center of those clouds, those are the centroids or centers of masses of each one of those classes. Okay, so that's the center, and so then I'm moving each one of those points, each one of those clusters, so that they are centered around the origin. So I'm pulling the blue cloud by subtracting the center of mass, so that this black dot here is going to be right on the origin. And so my blue points are now here centered at the origin. The red ones are pulled back to be around the origin. The green ones are pulled back to the origin. So rather than centering the whole data set, I'm centering each one of those subgroups separately. And so then pulling them back to be around the origin. So now all my data is sort of mixed up, and I put it in the same batch. So that looks like a counterproductive way to do, because what I was trying to do is I was trying to find the gaps between the data. But so this is a tool to make the data clusters to be as compact as possible. So you will see what that means. But so XW is now the data which you see on the right. So each cloud has been moved to the origin, around the origin. So okay, so this is my XW. So then I define the within cluster scatter matrix. So remember, scatter matrix was defined as X transpose. And so this SW somehow measures the spread of this cluster-wise centered data. There's another way of writing this SV if you like. This is not so useful, but you can do that. So you can take each one of those centered data clusters and write the scatter matrix separately, and then you take the sum of those scatter matrices. So this is another way of thinking. So you calculate the scatter matrix for each cloud, and then you sum up those scatter matrix. I like this notation because this is first doing the geometric sort of centering of the clusters, and then we calculate the scatter matrix. So this is the important formula. The first one is the important formula that you should remember. And the geometry, what is happening, is guiding the intuition here. Okay, so then what is how do I measure the spread between the clusters? So let's do the following. I'm taking the L cluster, okay, so XL, and then I'm replacing all my vectors in that cluster by the cluster centroid. So I'm building this rather uninformative looking matrix XL bar, which is just repeating the same vector over and over again. So it is repeating the cluster centroid. So this is basically this is a rank 1 matrix, because all columns in this matrix are exactly the same. So this is a silly looking, rather useless looking matrix. But what I'm doing now is I'm collecting all those cluster centroid repeated matrices into an X bar matrix. So the first cluster centroid is repeated P1 times, the second cluster centroid is repeated P2 times, etc. The kth cluster centroid Pk times. And so you see that the columns of this X bar matrix, there are at most k different columns in this matrix, because there are k classes. And so now I know that the rank of this matrix cannot be larger than k. So there cannot be more than k linearly independent columns in this matrix, because the columns are just a repetition of the same vector. And if these vectors are different, then I have k linearly independent columns, but it can be smaller too. And so then I'm doing the centering of this matrix. So I'm defining xc bar to be this low rank matrix x bar, and I'm subtracting the global centroid of the data. So C is the global centroid of all the data. Okay, so I'm making a matrix where I'm repeating this global centroid, and then I'm subtracting from each column this global centroid. So this matrix x bar C is basically measuring how much different the cluster centroids are from the global centroid. And the difference is repeated as many times as points you have in your clusters. Okay, so this is my auxiliary matrix. And now I'm defining, okay, so here's a picture what I did. So I took all of these clusters and I moved all the points into the center. So I replaced all blue points by the cluster centroid. I repeated all red points by the cluster centroid, and same thing with P's. And so then I have a data set which consists of 3 different data points. And this blue dot here is repeated as many times as I have data points in my blue cloud. The red dot is repeated as many times as I have red points in the cloud, and the green one similarly. So this is really a boring data set, because it's just repeating 3 different vectors. But the information is now how many times these vectors are being repeated. And so that gives different weights for these 3 clusters. So if you have a big cluster, there's lots of repetitions. If you have a small cluster, there's less. Okay, so so then I'm forming the between cluster scatter matrix. So I'm asking how far away these points, these blue, red, and green points are scattered from each other. And so I'm forming the scatter matrix. So I'm taking this xc bar transpose. And if you want to, so this is the formula that you have to remember. So then if alternatively, if you want to write it in different ways, you can write this. So there are 2 different ways of doing this. So you can take a sum L running from 1 to k, and you take PL repetitions of this rank 1 matrix here, CL minus C, CL minus C transpose. And PL is the number of points in that particular cloud. Or if you want, you can calculate this between cluster scatter matrix, taking these CL minus C's as individual points, which are sort of replacing the original points in the data set. So this scatter matrix is measuring the spread of the centroids. And as I said, centroids with large clusters having more weight, because this PL in that case is large. So if you have a huge cloud, then that huge cloud has more weight in the calculation of the spread matrix. Okay, so what could be the goal now? So basic idea in the LDA is so we want to find a direction in which our data clusters look as compact and small as possible, but those compact and small clusters are as far away from each other as possible. So there are 2 objectives here. So we want to make the within cluster spread as small as possible, so that the data looks really a compact cluster if you look at the within cluster. And on the other hand, we wanted the between cluster spread is as large as possible, so that the centroids of those clusters are as far from each other as possible. So we have these are kind of conflicting objectives, because one is trying to minimize something, the other one is trying to maximize something at the same time. And well, this is not an unusual situation for people working on optimization. You often have multi-objective optimization. So there are some features that you would like to make large and the others that you want to make small. And so there are different strategies to deal with that sort of multi-objective optimization. One possibility when you have just two objectives is just to look at the ratio of those numbers and trying to make that ratio as large as possible. And this is what we are doing here. So here's the idea. Think about the between cluster spread. So the between cluster spread is characterized by the SB scatter matrix. So therefore, if you want to maximize the scatter of the centroids, you would like to make this Q transpose SBQ as large as possible. And on the other hand, if you want to make your clusters to be as compact as possible, then you're looking at the within cluster spread, and that's given by Q transpose SWQ. And so you would like to make that number as small as possible. So now if I take the ratio of those two numbers, what I'm doing here, I'm defining a matrix, a function h of vector q, in which I'm trying to make the denominator small and the numerator large. So that is achieved if I make this h as large as possible. So I'm defining this this HQ in such a way that maximizing this HQ is somehow tantamount to achieving my dual goal of minimizing one thing and maximizing the other thing. So this is my tool to do that. So I'm defining this HQ, which is this ratio. It's a function of the projection direction Q, and I'm trying to maximize that. So how do I do that? So it looks like a complicated task. Turns out that we can do quite a bit of work using linear algebra. So first of all, sorry. First of all, I'm observing that if I'm scaling my vector q by a scalar alpha, you realize that this h function is homogeneous by scaling. So if I scale q in the numerator and in the denominator, I get alpha squared divided by alpha squared, and the alpha squared vanishes. So that means that my h is insensitive to scaling of q. So q can have length 1 or 1000 or whatever, and the h function is always the same. So h is depending only on the direction. And so therefore I'm going to choose a particular scaling of my q. I'm choosing my scaling so that the denominator becomes 1. So I'm looking for a q which is scaled in such a way that Q transpose SWQ equals 1. And if my Q satisfies this constraint, then my HQ is Q transpose SBQ divided by 1, which is only the Q transpose SBQ. And so therefore, I can rephrase my LDA problem of maximizing HQ by saying that I'm trying to find a vector Q so that it maximizes the numerator Q transpose SBQ subject to the scaling constraint that Q transpose SWQ equals 1. So I have reduced my problem into a rather standard looking constraint optimization problem where the objective function is quadratic, but also the constraint function is quadratic. And so that makes the problem at the end of the day a quadratic optimization problem, and it has a linear solution. So that's the good news here. So so let's see how you do that. So there are many ways to address this problem, and one way of doing this is use the Lagrange multipliers. So before I do that, I remind you of one result from linear algebra, which I'm going to use here. So this result is saying that if you have a symmetric positive definite matrix, I'm sorry, symmetric positive definite matrix, meaning that symmetricity means that the transpose of the matrix is the matrix itself. Positive definiteness means that V transpose SWV is always positive if V is a non-zero vector. So if these two conditions are valid, then we say that the matrix is symmetric positive definite SPD. And so this theorem that I'm going to refer to says that every symmetric positive definite matrix A admits a Cholesky decomposition. That means that the matrix can be decomposed as a product of K transpose K, where K is an upper triangular matrix with positive entries on its diagonal. So upper triangular means that K has non-zero entries only in the upper triangle. So entries on the diagonal and above the diagonal may be non-zero, and below the diagonal the entries are all zero. However, in this case, we know that the diagonal entries are going to be positive, and that is guaranteed because my matrix A is known to be here symmetric positive definite. And when you have this Cholesky decomposition, there are efficient algorithms to calculate it, and so you know that this matrix K is invertible, so you can always calculate the inverse of K because the diagonal entries are all positive. So now, I'm assuming here that my within cluster scatter matrix is symmetric positive definite. There is no guarantee that this is the case. And I developed the algorithm first with this assumption. At the end, I come back to this assumption and I see what needs to be done if this is not the case. So we do the algorithmic development assuming that the matrix is symmetric positive definite, and then we make a fix at the end if that is not the case. Okay, so if I give you a matrix and I'm asking, so first of all it has to be a square matrix. If I'm asking if it's symmetric positive definite, the symmetry is easy to check. So you just see if the matrix is a mirror image through its diagonal. So if you take the transpose, you get the same matrix. So symmetry is quickly checked. How about positive definiteness? So there is no simple way of checking if a matrix is symmetric positive definite. And in fact, this theorem tells you how you do it numerically. So if you have a symmetric matrix and you want to know if the matrix is symmetric positive definite, probably the quickest way to check that is to start calculating the Cholesky decomposition. And if your algorithm hits a snag, at some point it's trying to take a square root of a negative function, negative number, then you know that your matrix was not symmetric positive definite. So this theorem is almost like an operative check of if a matrix is symmetric positive definite. If you can calculate the Cholesky decomposition, yes, it's symmetric positive definite. If you can't, no, it wasn't. So this is almost like definition of the symmetric positive definite matrix. Some people even define symmetric positive definite matrices as those symmetric matrices which have the Cholesky decomposition. This is equivalent to matrix being symmetric positive definite. So this is good to remember. And so when you have a symmetric positive definite matrix, as I said, this matrix K is invertible. Okay, so we are going to use that, assuming that my SV is symmetric positive definite. So I start with the Cholesky decomposition. In MATLAB, if you need to calculate Cholesky decomposition, the command is CHOL, chol. So you take chol S and you get the matrix K. Okay, so that's one of the built-in linear algebra tools in MATLAB. So I'm assuming that I have now the Cholesky decomposition. And so let's look at the constraints. Remember, I'm scaling my Q vectors in such a way that Q transpose SWQ is 1. So I'm plugging in here my Cholesky decomposition of S, and I get Q transpose KQ. Well, this is the same as KQ transpose times KQ, which is the norm of KQ squared. And this was supposed to be 1. So I'm choosing my Q in such a way that K of Q is equal to 1. And what I'm doing here, I'm defining a W vector, which is this norm 1 vector, which is equal to KQ. And so I'm rephrasing my optimization problem. Instead of using this Q, I'm using my vector W. And so the LDA problem now in terms of W can be written as follows. Maximize the expression W transpose K minus transpose. So this minus transpose here means inverse transpose. So look at this formula here. W equals KQ. So I said that this K is an invertible matrix. So therefore Q is K inverse of W. And so I'm plugging here K inverse of W into this expression that I'm maximizing. And so using the fact that transpose of a product is the product of the transposes in the reverse order, I get W transpose K transpose inverse SB K inverse W. And so notice I'm using here this a little bit obscure looking notation K to minus T. So K to minus T means that I'm taking the inverse and then the transpose. If you wonder whether I should take first the transpose or the inverse, this is not a problem because the inverse of the transpose is the transpose of the inverse. And so you can first take the inverse and then the transpose, or you can first take the transpose and then the inverse. It doesn't matter. And so therefore this notation here is not ambiguous. It is exactly the transpose of the inverse. So this is the quantity that we want to maximize. And we have a quadratic constraint that my W has norm equal to 1. So you can think geometrically that W is a vector whose tail is in the origin and the tip is on the surface of the unit ball. So W is just giving a direction in the space. You are looking for a direction in which this quantity here is being maximized, and so you can think that this is a function which is defined on the sphere of a ball in n-dimensional space, and so you try to find the maximum of that function. I don't know if this geometric picture helps you at all, but I like to think in terms of geometry usually, so that's what I have in mind. Okay, so we need to maximize that, and so as I said, the tool that we use from constraint optimization is Lagrange functions and Lagrange multipliers. So I have one scalar constraint to be satisfied, and so therefore I'm introducing one Lagrange multiplier, lambda, which is a real number, and so then I'm forming the Lagrange function as they teach in the optimization classes. So you take the function that you want to maximize, which is here this WT K minus transpose SB K minus 1 W, and then you take minus lambda times the scalar constraint that you have. And so the scalar constraint is that W norm minus 1 is equal to 0. So this is my scalar constraint, and lambda is the Lagrange multiplier. And so again, using the ideas from constraint optimization, we are looking for the critical points of this Lagrange multiplier. And so among those critical points, we are hoping to find the maximizer. So this is the idea. And the nice thing is that now when I'm using this Lagrange multiplier, my function is a quadratic function. So when you calculate the critical points, meaning you're calculating the gradient of the function, and then you say that the gradient has to be 0. So that's by definition what critical point means in this case. So I'm taking the gradient of this L lambda W, and I'm saying that this gradient has to be 0. So the nice thing about a quadratic function is that its gradient is a linear function, and so then setting a linear function equal to 0 corresponds to a linear problem. So let's go and differentiate this quantity. So if you have an expression vector transpose matrix vector, and you calculate the gradient of that, it is 2 times the matrix times the vector. So this assumes that the matrix that you are using is symmetric matrix. So K minus transpose SB K minus 1 is a symmetric matrix, and so therefore the gradient of this quadratic form is simply 2 times the matrix times the vector W. What about gradient of the norm of W squared? Well, the norm of W squared, when you take the gradient, it gives you 2 times the vector W. So this tells you that the gradient, the norm of the vector is growing in the direction where the vector is pointing, right? So this is the outcome. And so therefore, if you want to find the critical points, you have to set this linear expression here equal to 0. And to make this problem a little bit more familiar looking, let's move this lambda w to the other side. So I'm canceling this 2 here, which gives no information, and I'm moving the lambda w to the other side. And so what we get is an equation saying that the matrix times w is lambda times w. And this is an eigenvalue problem. So you have a square matrix, which is a symmetric matrix, which is this K minus transpose SBK inverse. So that matrix times W is lambda times W. So what we are asking here is find the eigenvector W of that matrix. And then later we have to think which one of those eigenvectors you want. Because remember, this lambda is now the Lagrange multiplier, and we have to interpret what it represents at the end. I will do it soon, and actually I do it right now. So let's look at this expression. So suppose you have found an eigenvector W. So the W satisfies this formula in the box. Okay, so then let's go one step backwards. So remember, we are maximizing a function wk minus transpose sbk minus 1 w. So this is the quadratic function that we are maximizing. Now suppose that your w is now an eigenvector of this matrix with eigenvalue lambda. So then how does that function that we are maximizing look like? Well, I take the expression, and then I use the fact that lambda is an eigenvector of my matrix. So therefore, this expression reduces to lambda times W transpose W, which is the same as lambda times the norm of W squared. But the norm of W was chosen so that the W was chosen so that its norm is 1. So we see that the function that we are trying to maximize here is equal to lambda. So lambda, in case W is an eigenvector, will be equal to the corresponding eigenvalue. And so what does it mean? It means that we are looking for an eigenvalue problem where W is an eigenvector corresponding to the largest possible eigenvalue. And I'm ending today by showing you a basic results from linear algebra, and then next Tuesday we are continuing from here. So I remind you of this result. So if you have I refer it to the eigenvalue theorem. So this will help us to understand what's going on. So if you have a symmetric non-negative definite matrix, so that means that A equals A transpose, and V transpose AB is positive or equal to 0 for all of these. It could be 0 also. So then A has non-negative real eigenvalues. So if your matrix satisfies these two conditions, then the eigenvalues are all real, and they can be arranged into decreasing order, and all these eigenvalues are non-negative. And that's basically what we need to know. So what we are using this theorem for is that we have reduced the problem of finding an eigenvector for the matrix that we know here, which is this matrix, and we need to choose the eigenvector which corresponds to the largest possible eigenvalue, which is real. So we know now that our problem has a solution, because the matrix is symmetric non-negative definite, or positive semi-definite is another way of saying it. So we know that it has real eigenvalues, and we know that among those eigenvalues there is a largest one which we can pick, and that eigenvalue corresponds to the eigenvector, which is going to be our solution for the LDA problem. So it is now almost 5 o'clock, and so therefore I'm stopping today here, and so on Tuesday we continue with this, and we go to application, and then on Tuesday, let me give a small review. Then on Tuesday, after I have finished this topic, we are going to look at self-organizing maps. So that's the next topic in the in the sequence. So thanks for everybody for joining today, and see you on Tuesday then.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
See you.
See you on Tuesday.
Grazie, ciao.
Ciao, grazie.
Thank you. Goodbye.
Bye.
Bye. Bye.
Bye bye.
Ciao.
Oh.
Daniela, tu hai il microfono.
Okay.
Okay.
I just wanted to say goodbye to everybody
Okay.
and thank you to you, Erkki.
Thank you.
Goodbye.
Okay,
Goodbye.
see you on Tuesday. Bye.